We are solving question number 48 and 49 of GATE 2012 Chemical Engineering paper. So the common data for both the questions 48 and 49 is given as: for a liquid flowing through a packed bed, the pressure drop per unit length of the bed, that is delta P upon L, is given by this equation, where V naught bar is the superficial liquid velocity, epsilon is the bed porosity, dP is the average particle size, phi s is the particle sphericity, and rho f is the liquid density, and mu f is the liquid viscosity. And we have been given that the diameter of the particle is 10 raised to minus 3 meter, that is 1 mm. The sphericity of the particle is 0.8. Density of the fluid is 1000 kg per meter cube. Viscosity of the fluid is 10 raised to minus 3 kg per meter per second inverse. Density of the particle is 2500 kg per meter cube, and acceleration due to gravity is 9.8 meter per second square. Based on this, we have been asked two questions. So the first question is question number 48, which is: when V naught is 0.005 meter per second and epsilon is 0.5, which one of the following is correct value for the ratio of viscous loss to kinetic energy loss? So in the question, we have been given the pressure drop equation, that is 150 V naught bar mu 1 minus epsilon square upon pi square dp square epsilon cube plus 1.75 rho V naught square 1 minus epsilon upon epsilon cube phi s and dp. So the first term, you can see that the viscosity is present. So this, the first term, we can call it as viscous loss. So the first term accounts for the viscous loss, and the second term, you can see that we are having the velocity square. So basically that accounts for kinetic energy loss. And in the question, we have been asked to find the ratio of viscous loss to kinetic energy loss. That is basically the ratio of the first term to the second term. So we can write the ratio as 150 to V naught bar mu 1 minus epsilon square upon pi square dp square epsilon cube upon 1.75 rho v bar square 1 minus epsilon on 5s dp epsilon cube. So let's just cancel all the common terms. So we will be left with the ratio as 150 mu into 1 minus epsilon upon 1.75 rho. Then we are having this phi s dp and this superficial velocity v naught. Phi s dp and v naught. That is, we can write the ratio of viscous loss to kinetic energy loss as 150 mu 1 minus epsilon upon 1.75 into rho phi s dp v naught. Rho phi s dp v naught. Now we can replace all the values given in the question. So 150 into viscosity, mu is given as 10 raised to minus 3. 1 minus epsilon we have been given as 0.5 upon 1.75 rho phi s and dp we need. So rho is 2500. So rho, we need the density of the fluid. So rho f will be 1000, then dp is 10 raised to minus 3, phi s is 0.8. That is 1000 into 0.8, diameter was 10 raised to minus 3, and the superficial velocity v bar, v naught bar we have been given as 0.005 meter per second. So we can calculate this, and this ratio will come around 10.714. That is, for the given system, the ratio of viscous loss to kinetic energy loss will be 10.71, and we can select option C as the correct answer from the given options. Now from the same data, we have been asked this question number 49, which is, on further increasing the V bar, incipient fluidization is achieved. Assuming that the porosity of the bed remains unaltered, the pressure drop per unit length under incipient fluidization condition is dash. So this states that we were having a packed bed, and then on increasing the velocity until a certain point, that is after a certain point, this incipient fluidization is achieved. That is, the packed bed will become fluidized, and we have been asked to find the pressure drop per unit length under the incipient fluidization condition. So at this incipient fluidization condition, we can write the pressure drop across this bed of length L as delta P by L is equal to G 1 minus epsilon rho P minus rho F. Can again replace all the values. G we were given as 9.8, epsilon, the porosity of the bed remains unaltered, so earlier it was 0.5, so now also it will be 0.5. The density of the particles we were given as 2500, the density of the fluid we were given as 1000. So that is, you can write this as 9.8 into 0.5 into 1500. So this will become 7350. That is, the pressure drop across the bed at incipient fluidization will be 7350 Pascal per meter. So from the given options, we can see that option B is the correct answer. So we can select option B as the correct answer.